Welcome to the second part of Unit 6, Geometric Vectors, Lesson 5, Resolution of Vectors into Rectangular Components. We're going to do Example 2 and Example 3. Example 2 were regular components that are not horizontal and vertical. So we're going to start off with the example: a 20-kilogram wheelchair is stopped on a ramp that is an incline of 15 degrees. Resolve the weight into rectangular components to keep the, not the box, but the wheelchair at rest. The weight of the wheelchair is a force, and the force of the wheelchair is this: mass times acceleration. So again, we know that the force, I'll need that, is equal to mass of the object times the acceleration. Acceleration of what, Mr. Wills? Due to gravity. And of course, this is always 9.8 meters per second squared as long as we're on the Earth. For the wheelchair to be at rest, the force at work must be in equilibrium. That means that they have to have a sum of 0. That means when you add up all the vectors working on it, the overall vector would be the vector of 0. And again, equilibrium vector is one that balances another vector or combination of vectors. It's equal in magnitude, but opposite in direction. All right, so the wheelchair. So the wheelchair, here's the ramp. The wheelchair right now has this force of the mass or weight. And so I know this force is going to be, call this F, is equal to 9.8 times 20, which is equal to 196. So there's the first one. Now, of course, there's no other forces on it. This would fall through the ramp, and we'd probably have someone suing someone else. So there are two other forces on it. The other one is the force of the normal. The force of the normal is perpendicular to the ramp. This is a terrible drawing, Mr. Wills. Why? Because that's not really perpendicular, but this is what we call the force of the normal. And again, what is it? It is perpendicular to the ramp. And then we also have the force of friction, which is going up the ramp like this. So we've got this force as well, and that's called the force of friction. And again, because the force of friction is parallel to the ramp and the force of the normal is perpendicular to the ramp, I know that these two forces are at 90 degrees to each other. So that's going to be important, and again, that's called the force of friction. I have to rename some of these because I've got two F's here. So we'll do the force of friction, and this is the force of the mass here. And let's call this the force of the normal. So there we go. There's three forces. Okay, so I know that if I sum up these three forces, I get the sum of 0 because the wheelchair is at rest. Really important. Again, the wheelchair is stopped, so that means that the overall force, if I add up all the forces upon this wheelchair, it would be 0. So let's draw this diagram. Here we go. I'm going to start with this guy here. This is the force of the mass, which is equal to 196 newtons. Got the 6. And then I've got this guy here. Force of friction. Now the nice thing is I know that the force of friction, because it's parallel to the ramp, if I know if that's a horizontal, that's 15 degrees, then I know this guy here is 75 degrees. And then I've also got the force of the normal. And I know that the force of the normal and the force of friction are at 90 degrees to each other, because one's parallel to the ramp, the other is perpendicular to the ramp. So if this is 75, that's the normal. That means this angle, sum of the angles of a triangle, this has to be 15 degrees. So I've got this. Now what's the question here, Mr. Wills? You figured all these angles, you figured the side, one of the magnitudes of the side length. What's the angle? What's the question here? I want to know what the I want to know what the force of the normal is, and I want to know the force of the force of friction, the magnitude of the force of friction. So let's do we'll do the force of the normal first. The force of the normal is equal to, and again I can use that formula from before, since let's use this guy here. So that's going to be my opposite, that's going to be my hypotenuse, so I can use sine, and sine of 75. So I know the force of the normal is going to be 189.3 newtons perpendicular to the ramp. I also want the force of friction. So this is going to be 196. Again, I'm still going to use this angle. So that means I've got the adjacent and the hypotenuse, so that means I'm going to use cos of 75. So the force of friction is going to be 50.7 newtons. This is a classic test question. I love putting these on tests. Again, it's all about drawing the diagram, then redrawing the diagram so that everything is tip to tail, because you know that some of these three vectors is 0 because the wheelchair has been stopped. Once I do that, then I can use the formula from the beginning of the lesson. Again, I'm going to use the force of the normal here, because if I use this angle here, that's my opposite of my hypotenuse, so I'm using sine. And then if I'm using this angle here again, this is my adjacent of my hypotenuse, so I'm using cos. Alright, and let's finish off this by looking at rectangular components that are not horizontal or vertical, and here's a traffic light at an intersection. So same questions, last question from lesson 4. Exactly the same. A traffic light is hanging at an intersection, and traffic light at an intersection is hanging from wires at equal length that make a 10 degree below the horizontal. So I know these are 10 degrees. The traffic light weighs 2,500 newtons. What are the tensions on the wires? Note, the tension is an equilibrium force in a rope or a chain keeping the object in place. Again, same thing as here, right? My wheelchair is not moving, so same thing here. The traffic light is not moving either. So how do I do this? Again, I'm going to redraw my vectors just like I did before. So I'm going to draw, again, this is going 2,500. Let's call this tension 1, tension 2. So what I want to know, I want the tension on the wire. And again, because they're at equal length, now sometimes they won't be at equal length, but because they're at equal lengths, I know that the magnitude of T1 is equal to the magnitude of T2. Alright, let's find the tension of the wires. So again, I'm going to redraw my diagram. So here is my 2,500 Newton. I've got this guy here. I've got this guy here. Please excuse me if this is not perfect. There we go. But if I split it in half again, since this is 10 degrees, this is 10 degrees, and what I can do, that's 90 degrees, what I can do here is I can just pull out a triangle. One of these triangles, since they're equal length, I know that the magnitude from here to here is equal to the magnitude from here to here, and the total magnitude is 2,500. So I'm going to pull out a triangle here. Again, I've got this, I've got this, and I've got this. And I know this is going to be half. So I know this is going to be 1,250 newtons. This is going to be 10 degrees. And I want to find this out. T, what do I call this one? Doesn't matter. I call this T2. So I want to find the magnitude of T2. So how do I do that? Well, I've got opposite, I've got hypotenuse, again, because this is a 90-degree angle. Again, I split it in half. So I know that sine of 10 degrees is equal to 1,250 over magnitude of T2. So that means T2 is equal to 1,250 over sine 10, which magnitude of T2 is equal to 7,198.5 newtons. And there we go. And I know that that's also equal to, which is also equal to T1, the magnitude of T1. Therefore, tension on both squares is 7,198.5 newtons. Below is horizontal. 1 to the right, and 1 to the left. Done. And that is geometric vectors.